So this video lesson is all about ratios and rates, and we're going to go through sort of one by one with ratios and rates. What is a ratio? How do we use it? What does it represent? What are some things that it's similar to that we've seen before? How a rate then relates to ratios, and then of course at the end there'll be some practice problems for you to look at, and we'll go through the answers after you look at it and pause the video and go through it. But the first thing that we want to look at is first, what is a ratio? And to talk about a ratio, let's start with something concrete that we can see. We'll start with some Skittles. And the reason we're going to start with Skittles is that there are different colors of Skittles in packets. And so let's say we open a packet and these are the numbers of each of the different colors of Skittles that we have. We have 12 red Skittles, 12 green, 9 purple, 11 orange, and 15 yellow. So I'm going to give you a few examples here of the way that we use ratios, and we'll use those examples to draw on a definition of what a ratio is. Well, one of the ratios we have is, we look at it, we have 12 red Skittles to 9 purple Skittles. We have a ratio of 12 red to 9 purple. We have a ratio of 12 green to 15 yellow. That's tough to see there. And we have a ratio of 11 orange to 12 red. So based on all of these, and I've drawn them with colons specifically and for a reason, based on all of these, we can take a guess at what a ratio really is. And in this case, we're comparing the number of red Skittles to the number of purple Skittles. Here's the number of green Skittles to the number of yellow Skittles. And here's the number of orange to the number of red. And that's really all that a ratio is. A ratio is just a comparison of two numbers. Now we can compare numbers outright, the ratio of 12 to 9, but more often it's put into a specific context, something that we can understand. Say in this Skittles example, there are 12 red Skittles for every 12 green Skittles that are in this bag. So let's look at a few different ways of writing ratios. I already wrote it down as a colon. What that colon means, and the way that we read it, is using the word to. And we can write it that way too. There are 12 red to 12 green in the bag, just comparing the number of red in the bag to a number of green to the bag, and there are 12 red for 12 green written as a fraction. And in the definition and ordering of rational numbers, we talk about a ratio very quickly as a fraction. There's nothing specific there and nothing you need to look at, but if you've seen it there before, then this setup should be familiar. But all it is a comparison of, in this case, the number of red Skittles in a bag to the number of green Skittles in a bag. 12 red to 12 green. 11 orange to 9 purple. 15 yellow to 12 red. All of those represent ratios of the number of each type of Skittle in a bag. Now, of course, the natural question that comes up with seeing that the ratio is written as a fraction is, can we reduce the fraction the same way that we reduce equivalent fractions? And the answer is yes. There are things called equivalent ratios that represent the same value. And some examples of equivalent ratios are, in the left-hand case, 9 purple to 15 yellow is the same as 3 purple for every 5 yellow. And as you can see, they operate exactly like equivalent fractions do. That is, if we multiply and divide both parts of the ratio by the same number, we will get what's called an equivalent ratio. They represent the same value. In the case with the purple and yellow, where we're looking at them already as a fraction, it's obvious that because we multiplied, or rather divided, numerator and denominator both by 3 in this fraction, that 9/15 is the same as 3/5 from a fraction, so a ratio of 9 to 15 is the same as a ratio of 3 to 5. And what this new ratio represents is not that there are 9 purple, not the same as the other one where there are 9 purple in a bag and 15 yellow in a bag. It represents that in the total amount of Skittles, for every 3 purple, there are 5 yellow. They come in a ratio of 3 to 5, of 9 to 15, and they are the same ratios. Now I added the example of 12 red to 12 green on the right hand side, so you can see that even if we don't write the ratios as a fraction, we can still talk about them in terms of equivalent ratios. So 12 to 12 is the same ratio as 1 to 1. 12 red, 12 green represents that for every red, we can find a green in the bag to represent it. And unlike fractions, this is important, we are allowed to have decimals and fractions in our ratio. Now, it wouldn't make a whole lot of sense to put a fraction within a fraction, so don't, if you use a fraction in your ratios, don't put a fraction into a fraction. But whereas 9 purple and 5 yellow, we would put it into simplest form in fractions, which is 3 purple to 5 yellow. But here, we can reduce it even further, and if we want to make it out of 1 yellow, we can say it is 0.6, because that is 3 divided by 5, and that's how you take it from 3/5 to 0.6 over 1. This ratio still works, because this is a ratio and not a fraction, as we've talked about them before. And the last thing I'll say about ratio is that order is important. 9 purple to 15 yellow is not the same as 15 yellow to 9 purple. They are opposite ratios. And so now we get to the idea of a rate. And a rate, quite simply, is just a ratio between numbers that involve different units. In the examples before, where we talked about Skittles, we were talking about 12 red Skittles. Our unit, for what it was worth, was Skittles in every case. However, when we talk about a rate, normally we do something with time. 24 miles an hour, 24 miles per 1 hour. A faucet, a particularly powerful faucet, spends 11 gallons in 30 seconds. Something crawls or moves 98 meters in 20 minutes. Now this is still a ratio because it compares miles to hours, gallons to seconds, meters to minutes, and it compares those two numbers so we can understand, okay, well in 20 minutes, something moves 98 meters. Well, because they have different units, miles per hour, gallons per second, that word per is important when it comes to rates. That's how we show which unit goes in the numerator and the denominator of the fraction, which goes first and which goes second. Miles per hour, gallons per second, meters per minute. And so just like in ratios, we have these things called equivalent ratios, we have the same idea with rates, but we extend it so that we see any rate that has a denominator of 1 is called a unit rate. This is where we see things like in miles per hour. 24 miles per hour really represents that you move 24 miles in 1 hour. So 60 miles per hour represents 60 miles in 1 hour. 60 miles per hour. That is a unit rate. So just a quick review of all the definitions we've come through, because there are a whole bunch of different things, but we'll go back and review this here. A ratio just compares two numbers, and we write them using either colons, a 2, or using a fraction bar. And equivalent ratios, like equivalent fractions, represent the same value. A rate is just a ratio that's between numbers with different units, and we call something with a denominator of 1 that we would call an integer with numbers, or a fraction in simplest form. We call that a unit rate. So let's take some time to practice this. Go ahead and pause the video and see if you can just write the ratio of, for 1, 2, and 3, the different Skittle colors, and they're reproduced here, and in 4 and 5, write the rates, not as unit rates or equivalent ratios or anything like that. Just write, what are these? What are the ratios and rates in the forms that you see them right now? So let's look at this. An orange to green, there are 11 orange to every 12 green, so orange to green is 11 to 12. As writing with the words 2. For yellow to red, there are 15 yellow for every 12 red. Now I wrote it with a fraction sideways just for the amount of space here, but the idea is the same thing, 15 over 12. And purple to red to orange. Now if you were a little bit confused by this, that's perfectly fine, but all you do is take that word 2 and use it. In this case, I'm going to use it as a colon so you can see the other example, but there are 9 purple to 12 red to 11 orange. And that's all it really is, comparing 3 numbers all through a ratio. Now, in this case, you probably wouldn't want to use a fraction bar for this. You'd want to use either the word 2 or the colons. So for 4 and 5, you travel 17 miles in 15 minutes. And a faucet uses 12 gallons in 5 minutes. Now, if we're writing just a ratio, or excuse me, if we're writing just a rate by itself, we like to include the units because it tells us exactly what it is that we're comparing. And now finally, for 6, 7, and 8, let's find some equivalent ratios. Give me an equivalent ratio for the green to purple. Tell me what the ratio is and see if you can find something that's equivalent. And the same for red to yellow for 7, and then you're going to find the unit rates for miles and hours in A and meters and seconds in B. So write the original ratios and rates and then find either equivalent ratios or unit rates. So the ratio of green to purple is 12 to 9. I'm going to write it as a fraction so we can see the relationship to equivalent fractions. And so I'm going to divide numerator and denominator by 3 and get 4/3. Or maybe I should multiply numerator and denominator by 2 and get 24/18. Or just maybe I should divide both by 2 and get 6 to 4.5. All of those are examples of equivalent ratios, as long as you multiplied and divided numerator and denominator, in this case, by the same number, decimal, fraction, or integer. It's correct. Red to yellow is 12 to 15. Another few examples are 6 to 7.5, and 4 to 5. But again, as long as you multiplied and divided by the same number, you've got the idea here. Now the rate for 8A is 70 miles per 2 hours. We want to make that denominator into a 1 because that becomes a unit rate, so we divide both by 2. We end up with 35 miles to 1 hour, or 35 miles per hour. If we have 45 meters in 10 seconds, and I will write this in a colon, just as an example. We usually write rates with a fraction, but we'll write it with a colon because we can do the same thing. Divide by 10 so that your denominator, or the second part, is 1. You have 4.5 meters per second. So as a way of review, a ratio is a comparison of 2 numbers represented with a colon, the word 2, or a fraction bar. Equivalent ratios, like equivalent fractions, represent the same value. A rate is just a ratio with numbers of different units, whereas a standard ratio compares things of the same unit. And a unit rate is just a rate that has a denominator of 1, or the second number in the comparison is 1.